the air canister for one of the like one of the pneumatic air canister things on 254's robot this year was just like zip tied to their tubing. It's really
I'm
funny.
glad that that's the first thing that's on this recording.
Oh yeah.
All right, so we're gonna go ahead and get started. I don't know how long this class is gonna be. It might be short, might be long, depending on how many questions people have. Um, this one's not math heavy or anything. It's just sort of general stuff because I wanted to do sort of a class that could work for anyone. 3 of you have been to most of the classes anyways, but Josh, you've not been at them, so that should be pretty good for you. So first off, we're just going to do general suggestions in the class that like in the actual course we're going over motors and gearing right now. We're just sort of doing some general bits of it. So I wanted to go over some of that. And this is not going to be like hard information, like it's not going to be numerical for the beginning. It's just like suggestions, mostly in like prototyping stages, however also just in design. So this will be recorded and you can look it up, but they're kind of just like general tips, tricks, stuff like that. Some of you probably already know. This one's just general suggestions having to do with motors and gearing, which is basically when you're working on your power transmission, which is like your gear train, whatever you want to call it. Always control the top speed of that operation or whatever you need your torque output to be with gearing and not reduced voltage. A lot of people will either reduce the amperage or voltage to sort of control how fast the motor's going. You know, on a drill, how you can like press it halfway and it'll go slower. That's doing that. It's always better to do proper gearing as long as you have a situation where you can do that. In sense of like, if you have your drivetrain and you want to go 1 speed during your autonomous, let's say, use gearing to make it that speed. Don't just lower, don't just change your power input, because if you do that, you're going to be running the motor either at low efficiency on the left side of its curve, which we talked about a little bit, or you're going to be running it over on the right side of the curve, which is going to make the motor very unhappy. But basically that's just a general tip. Some things to keep in mind, and we talked about this, and we can look at some examples too if you guys want, but avoiding powered anti-backdrive, which I see a lot in FTC. People tend to just do powered anti-backdrive, which is like you're climbing up and then your robot just slowly starts to fall as like the match ends, because the only thing holding it up is the motor itself. If you can design something that will keep it from unwinding without having to power the motor, that's way easier on the whole system. It's easier on the motor, so you're not going to burn it out as quickly, and the motor is going to last a lot longer. Some ways to do that: worm gears are anti-backdrivable, like we talked about. A mechanical one-way clutch is a way, and a retractable ratchet is a way. A ratchet also doesn't have, you can make it non-retractable. The problem with that is you can't reverse it if you want to. You can't power it in the opposite direction.
That makes a lot more sense, because I thought that bullet point was like listing things to not do.
No.
That makes more sense.
Fair.
In FRC, we pretty often just like stick a ratchet wrench on the axle we don't want to like back drive, and then have a solenoid that like you can release it so that it can back drive.
Right. So that's a retractable ratchet. You're just using a pre-built one.
Yeah.
Which is a great way to do it. If you buy a little bitty ratchet wrench, then you could put that on a FTC robot, and a lot of them have a lever on the back, you know, to switch which way it ratchets. You just put a servo to flick that. That would work fine too.
I am actually planning on in CAD zip tying a ratchet wrench to a mechanism to use as a one-way clutch. So like you can't be above that.
Alternatively, instead of zip tying, you could design it for it.
Yeah, or you could like mill out holes in it, or
Well, it'd be easier just to 3D print a mount for part of the handle and then like chop the handle short.
yeah. I mean,
But yeah, that's one way to do a easy retractable ratchet. One-way clutch and stuff like that. I mean, you can design them. I don't think there are any that are like just pre-made that you can buy for FTC. I'm sure you could buy a small one and use it for FTC. But those are some ideas if you, especially with climbers, like, you know, where you need to hook onto something to climb up, definitely use that. It will make your robot's performance leagues better, and also you won't have to swap out your motor. We have a lot, or at least we used to have a lot of bed motors, and that was probably a large contributor to that. Generally, overrunning motors is why, but that's a good way to overrun one.
oh yes. So I don't know how relevant this is right now, but I also don't know if it will be more relevant later. You can use brushless motors in FTC if they are sold to you as a servo. That is a loophole in the rules that allows you to use brushless.
Yeah, I did go through all the motors, and we'll talk about that in a sec. You can.
But there's also a voltage limitation, so it's not.
I would highly recommend just doing a mechanical fix for those sorts of problems and running your motors correctly. Gearing is super important, and you're gonna need to know it, especially if you go into robotics or mechanics or anything like that. And it's best just to learn how to do it properly early on, instead of learning how to do it wrong and then being like, this is fine, and then somebody in industry is like, no, it is not. You need to rethink this.
Also in FTC, there's just no reason to use brushless motors.
Yeah. So another thing, and these are kind of sort of common sense, but you know, to each their own, especially in prototyping, just because it'll make your prototype work. A lot of people build a prototype, but they don't know what they're doing, and you end up with something that just doesn't do what it's supposed to. High RPM, which if you don't know, RPM is rotations per minute. It's how fast a motor spins. High RPM applications, so things that are going to be fast spinning, are great for shooters. They don't need a lot of torque, which is like how hard it is to twist something, or how hard a motor twists something. They don't require a lot of torque. Intake systems also don't usually require a lot of torque. Fans don't really happen a lot in FTC, but later on, when you do stuff like that, fans are nice to know kind of how to build. Those are all really high RPM things that don't require like almost no torque. Shooters require the most out of those three. Fans require basically zero, just enough to move whatever it is that you're putting on there, whatever prop. And then high torque is the opposite. There's a trade-off between RPM and torque. So the more torque you have on a certain motor, the less RPM you'll have. Good things for that are like lifters and arms and climbers, anything that's got a lot of load, a lot of weight that it's trying to pull or move in some direction, but doesn't need to be particularly fast. There are middle lines in both of these. So these are just general things of like, this is kind of what you should use it for. If it's a climber, try to go high torque, and we'll talk about this more. We've started talking about this in the actual class, but if you do, you can do some calculations to figure out exactly how much power you need to be outputting, which means how fast you can lift a certain weight a certain distance. So if you do those calculations, which if you watch the last lecture, you should know how to do them, you can get your robot to climb as quickly as possible, as efficiently as possible, which is the ideal scenario. Because if you want your robot to be able to climb very quickly at the end of the match, like you just want to drive over, grab on, and zip up, then you can optimize that situation mechanically before you even get on the field. And it's maybe 30 minutes of calculation. They're really easy calculations. It's basically just multiplication. As long as you know general units, you're fine. That lecture is going to go up soon, so if you want to watch that one to know how to do it, it'll be posted. You can also use the same calculations for lifters and arms. It's the same idea. It's just not lifting the whole robot. But those are high torque things. But usually you want the highest RPM with the amount of torque that you need. So yeah, servo applications, I think you guys kind of know this. They're little to no load. They're not usually very powerful. We do have some high torque servos, I think, but it's only a couple of them. And it's really not necessary. They're good for precision and things that are degree based because, you know, they monitor their position. Yeah, that one's pretty common sense. Any general questions on these little things?
None here.
Cool.
No.
So this is just something I thought would be interesting. I did a quick, this is the dumbed down version. I did the full table for each one of these motors, which in previous class we've talked about that. There's performance maps for motors, and it's basically how much torque and how much RPM and how much power they can output with a certain efficiency and certain current. So, but this is the dumbed down version. This is all of the legal motors that aren't servos. And I just sort of compared them together. And from what I understand, you guys are using GoBuilda now, which is great because those are the best overall. And the reason they're the best overall is, I don't know if you guys can see my cursor here, but when you look over here at the gearbox, you'll notice that they have a variety all the way from 188 to 1 gearing through 3.7 to 1 gearing, whereas the others basically only have 2 options. That variety is really important because if you look over to the left here, you can see their no load RPM is just how fast it spins with nothing on it. It's also called free run speed, but you know, you can see that its no load RPM is actually lower than basically everything else. And its stall torque is a little higher, but not by a lot. And the reason that it's better in general is because it has more gearing options and more gearboxes. So theoretically, though, if you wanted to, you could gear an Andy Mark motor to make it faster than a GoBuilda motor, which I think is interesting.
Andy Mark actually sells Neverest 3.7 to 1 gearboxes.
Yeah, that's kind of what I'm saying is if you wanted, so the standard motors, like you can buy a 41 and 60 to 1 just already put together. If you want to buy a 3.7 to 1 planetary gearbox for a Neverest and put it on the Neverest, you can do that, and that will be faster than the GoBuilda. But the pre-builts, the GoBuilda is the easiest variety option. I've also noticed, generally speaking, the FTC motors are all pretty mid-range, pretty similar, which makes sense. But if you do want to maximize that sort of thing, it's something to note. If you also see install torque right here, which is how much torque the motor can put out at its maximum before it stops being able to push.
Wait.
Yeah.
Does Tetrix not have gearboxes on their pre-built motors?
So Tetrix, when I was looking up, and I'll actually show you guys, here are all the spec sheets for the motors. Tetrix, its spec sheet is terrible. You probably don't know what, I mean, you can look at it, it's a spec sheet, but typically motor spec sheets will show their stall current, their no load current, their no load RPM, and their stall torque. Tetrix decided to not do that. Instead, they did their load current and their load torque, which is not at stall. It's just a load that they sort of chose. It's probably its rated load, which means it's peak efficiency, basically. But it's really hard to tell with their spec sheet layout. It's not great. And what I've noticed is from using the Tetrix motor and what this says for the Tetrix motor do not line up. Theoretically, the Tetrix motor should be the best motor out of all of them, but it is definitely not. And yeah, and one of the reasons for that is because there's no gearing, but secondarily, I have a strong feeling that they are maybe buffing out their stats a little bit on this spec sheet.
Yeah, because like I've seen Tetrix motors used, and there's no way that they're better in any way.
That's what I'm saying. Is I looked through everything, and they're what they're listed as on this spec sheet is there's no way in, like there's just no way that that's what they actually are. So I'm not fully trusting of Tetrix. I do know that they are, in comparison to other FTC motors, pretty high torque, which was represented on the spec sheet. But the problem with them is that they aren't geared. So if you buy a Never Rest motor by itself, it's not very big. It's a pretty small guy. Tetrix is also pretty small, and the reason why is because there's no gearbox. If you put a gearbox on a Never Rest, it becomes the longer Andy Mark motor that you know. If you were to put a gearbox on Tetrix motor, it would also be a similar size. So if I don't know whether or not there are pre-made or pre-built planetaries or orbital gearboxes for Tetrix motors, but if there are, it could be interesting to try them out because you might be able to use it for higher torque applications. And you could see pretty good performance out of it. I know that by itself, the Tetrix is not worth using. And its biggest downfall is that it doesn't have easy gearing. So
I would assume the gearboxes are cross-compatible, because I know like you can stick
depends. It really highly depends.
You can stick a Never Rest gearbox on a Neo 550.
The problem is that companies like to make it so where they're not compatible, so that you have to buy their gearbox. So you just have to check.
Yeah.
But if you wanted like a fun, like just a sort of little interesting project to do that wouldn't take very much time, try putting one of those other gearboxes onto a Tetrix motor. You'd have to finagle a little bit, but if you did that, you could run some tests to see how much torque and RPM you can get out of it. Because based off of its spec sheet, the base motor is actually better. I don't know if that spec sheet is honest, but
yeah, I highly doubt that.
I highly doubt it as well, but still. Another things to note, so the Go Build-A motors are by far the largest of the motors. But they do give the most variety, the highest torque, and the highest RPM generally. However, the Never Rests, if you got different gearboxes and attach them yourself, they are better for RPM if you want speed. If you want torque, just go with the Go Build-A. They're better than everything else. The second best overall, if you're just using the pre-builts, is actually the Rev Robotics HD Hex. So that's the one with the hex shaft output. It's just got middle line stats, but it is significantly smaller than the Go Build-A motors. So if you wanted something that was pretty solid, you didn't need much higher torque or much higher RPM, then you could definitely use one of those for it if you were tight on space. And then this one's just interesting, and I know, Jude, you probably know about it. I don't know how many of the rest you do, but the Rev Robotics Core Hex motor, is it's got a 90-degree output shaft. So what that basically means is that there's and it's a female output shaft. So it's the motor, and then there's a hole going through the motor that you can put a axle through, or a shaft, and it's kind of a flat motor. So if you wanted to, that'd be a very easy thing to mount for a drivetrain. That stacking up wise, it's got a lot lower torque than most of these other motors, but its RPM is higher. So
is it the like sideways one?
Yeah, and actually, if you want, I can show a photo of it real quick.
Project Peacock used one on our robot this year, and like, don't use them. They like, anything you can do with one of those, you can do with 2 servos.
It's fair. So I don't know if can you guys see this screen?
Yeah.
These
Yes.
motors. So this guy right here is the Rev Core Hex. The one above it is the one I said is second best, the HD Hex, which is pretty middle line. And then you guys are using this Go Build a Guy right here. These are the Neverest. And then, of course, your family favorite Tetrix.
Oh yeah. So are you gonna get to Rev Ultraplanetary gearboxes?
Probably not. We can look at them if you want to.
Those are fun because you can do anything from 2 to 1 to 60
Yeah.
to 1.
They're solid. The Go Builda does have a larger range
Yeah.
of gearings, which is nice. I don't know if it's really necessary, honestly, but it is nice.
With the Hex, or wait, the Ultraplanetary, you can buy the modules on their own, so
Yeah.
you could easily turn the 60 to 1 into a 120 to 1.
Yeah, stacking gearing is pretty easy to do. So you could definitely, I mean, you could do similar things with a lot of these. If you wanted to put a little gear train or a little like custom gearbox on the end of a Go Builda motor, you could up its gearing too.
Yeah,
not hard to do. You would need to know, and we're going to go over that here in a sec, just generally how to do that kind of thing. But you can definitely buy modular gearboxes and stack them.
I think you can stick Ultraplanetary on. So I know it works with all the Rev motors except for Core Hex, and then So and then it works with Neverest, and I think also Modern Robotics.
So my general recommendation, because it sounds like you guys have Go Builda motors now, is to use Go Builda's motors anywhere you can. If you're tight on space, maybe check out the HD Hex, the Rev HD Hex, and I would be interested. I would challenge somebody to, in a prototype, try using the Rev Robotics Core Hex and maybe some gearing to try to build a shooter, because its RPM is significantly higher. Like its free load RPM is significantly higher than the other motors, and if you geared it right, it could have a much higher output of so like if you're shooting balls or something like Velocity Vortex, you could have a higher fire rate, which I think would be interesting to check out. So if somebody wants to just try that on their own, I would test it out and see how it backs up against a Go Builda motor.
So if you like compare it to stuff people have done, Steven with his off like gluten-free with their off-season robot, they did 3.7 to 1 Andy Mark motors, and they did 2 of them for their single flywheel shooter.
Mm-hmm.
So that makes me think the torque might, like, you might need the torque.
Well, it depends on what kind of shooter you're building, especially because if you say it's like I don't know if any of you watched much of FRC, but if you have a softer ball, like one of those squishy ones, like a dodgeball, you have to put a little bit of pressure on it to get it to do basically anything. And if you need to put pressure on it, you're going to have to do either torque calculations or some kind of guess and check with it to see if it's going to be able to, because once the ball hits, if it's like a wiffle ball, it's got a set diameter, and you can have it so that the wheel just nicks it, and high speed is great and you'll need lower torque for that. If it's a squishy guy, then you're more likely going to need a little bit higher torque, which that depends on the challenge and depends on the shooter, but I would be interested just for someone to try with a hard plastic or like a golf ball or something like that, just to test those two motors against each other. The Go Builda and Core Hex.
FRC is great because you can just like slap a huge brushless motor on it. And
I mean, FRC, you got a lot more power. I'd also be interested if someone wants to try to gear a Tetrix motor to see how much torque you could get out of that in comparison to the Go Builda motor, because you might find out that Tetrix has an application, which I think would be hilarious to find. But so those are just the general inclinations on the legal motors for FTC. I'm not really going to go over servos, because the thing is with the servos, you basically have one kind of servo that is common, and you can do other things, but it's not really a point to with servos. The servos that you get, I think they're Modern Robotics, are fine. They have enough accuracy. Servos are more of an accuracy thing than they are a torque or RPM, so I wouldn't worry about those.
There is a servo that circumvents a bunch of rules. That's basically it's called the Aussie Boards Super Servo, and to my understanding, it's basically a Tetrix motor.
Yeah. I mean, you can basically make a servo if you have an encoder. All right, so this is just some general stuff on gearing. We've gone over this in class, but I do want to just mention it here in this sort of overview guy. So first things first is what a lot of people call gear ratio, or gear train or speed ratio, whatever you want to call it. When you're doing, thank you, slides. When you're doing the equations for a gear ratio, typically it's written as E. That's just like the general gear ratio is E. You'll see a lot of people write the gear ratio like this, where it's like 2 to 1. You could also write it as gear ratio equals 2, or down here where it's 1 to 2, you could write it as equals 0.5, because it's actually 1/2. So when you're doing the actual equation, E is the notation for the ratio itself, and it is defined as all of these things. So you can see that down here. This is the full thing. But basically, it is defined as E, which is the gear ratio, is equal to the number of teeth on the gear for the driver, which is this guy. It's the one connected to the motor, or the closest to the motor, divided by the number of teeth for the driven, which is this guy, which is the one away from the motor, closer to whatever load you're trying to do. That is also equal to the angular speed, which is the RPM, of the out over the angular speed of the in. This is the in. We'll also write drivers. And this is the out, which is driven, which is also equal to the torque in over the torque out, which you can tell that these two equations, the speed and the torques, are opposite of each other, which just shows that the converse relation between them. And then efficiency here, you don't really need to worry about an FTC, but basically it's how efficient the gearing is. or the just the efficiency of the whole system. So like if you have friction and an axle, that'll cause your efficiency to be lower. Typically, people just kind of assume it to be like 0.95 if you don't really care. Which in FTC, I would just pretend like it's not there altogether. But basically, what this here is saying is the same thing as this equation up here. And that is just the gear ratio itself. So if you want, you could say, in this example, the number of teeth on the driven is 20 divided by the number of teeth on the drivers, which is 10. That equals 2. And that is what we have over here. So you would write 2 to 1. Easy stuff, but good to know. And if you have multiple gears and more stacked gears, then you always just go with the one. So the driver is always the one furthest or closest down the line to the motor, and the driven is always the one farthest down the line towards the load. And you can just add them all up. You don't have to like do one and then do the next one and then do the next one. You just take all the drivers, add their teeth up, and all the drivens, add all their teeth up, and then you divide. Similarly, you can do the speed out and speed of torque. So what's nice about this is I can say, okay, I've got a 10 tooth gear and a 20 tooth gear, and I know that my input here is, I don't know, let's say 30 RPM. Then I can say that 30, which is my speed in, and we want our out, equals 2, because that's what we got up here. So then we can just say, okay, that means our speed out will be 60 RPM. So it's a quick, easy way to figure out sort of like the in and out of your gear train. So all that's not too hard. If you want to go full into it, you can go watch the previous classes. Quick notes down here. Gears are compact, but they're inefficient. There's a lot of friction. There's a lot of binding. You only have 2 points of contact usually, like 2 teeth are touching, so they're not very efficient. Chains and sprockets, which are similar in their equations, are more efficient. They have many points of contact. Everywhere the chain touches the sprocket is a point of contact, so more force is able to be transferred through. So they're much more efficient, but they're usually large. So if you don't have a lot of space, you want to go with gears. If you do have a lot of space, chains are good. Especially if you're going a long distance, always use a chain, don't use gears. Belts, they're good for high RPM applications usually, but they can slip, and you definitely don't want to use them for torque because they will slip. So if you want something to spin real fast and you don't want a bunch of load on it, a belt is a totally viable and pretty good option.
In FTC, generally, if you have the spacing right, belts aren't going to slip that much.
Yeah, that's true. There's usually you're not doing anything with high enough torque, but I don't know why anyone would try to do this, but if you're trying to like power a winch for climbing with a belt, it will slip.
Yeah, I mean,
you know what I mean.
In FTC, belts are generally better just because they're like super light.
Belts are nice for a lot of applications, like an intake would be great for belts. A shooter could use belts, a sort of like transfer system, so like moving like a game piece from one end of the robot to another end, that's good for belts. But using them for anything that is of high torque, FTC does not have high torque really other than climbing, but try not to use belts for that. A chain, you can get chain in FTC that is similar in size and weight to a belt, not wholly that different, and it'll be a more efficient system, so you don't have to run the motor as hard, which means the motor will last longer, which means you need to buy parts less often. So it's a thing to keep in mind. I'm going to clear the drawings on this unless anyone has a protest. Cool. All right, and we will keep going. So I asked during Thursday if we wanted to do just a quick overview of statics, and I got not a resounding yes, but a yes. So we're just going to do a quick review of it. Biggest thing is just Newton's 3 laws. If you've taken a general science class at some point, you should have at least heard them or heard them from somebody at some point. Basically, object remains at rest or continues to move at a constant velocity unless acted upon by an outside force. That just means if it's sitting, it's going to stay sitting until something else pushes it or something else does something to it. If it's in space and it's moving, it'll keep moving until something else hits it. Force equals mass times acceleration. Second law. Basically, that's the most important one for statics. It's F equals ma. So mass is not your weight. It is inherent quality based on basically, it's related to density. It's not based on it, but it's an inherent quality to certain particles. Acceleration can be a lot of things. Gravity is an acceleration, but it's basically how fast something, it's not how fast something's moving, but it's how fast it's changing how it's moving. So it's speeding up or slowing down. And then force is mass times acceleration. Weight, your weight is a force. Pushing on something is a force, etc. All forces have an equal and opposite force. That's super important for statics because that's how you draw free body diagrams. So basically, it's if an object is sitting on a table, the weight is pulling down, but it's not falling down, so obviously something else is pushing up on it, and the table is what's pushing up on it. The bonds of the table are not breaking, so they're holding it up, pushing up on the object. Thing that tended to be a sort of concept that people had to wrap their heads around is just mass and weight are different. Weight is a force. It is mass times gravity, so they are separate things. Mass does not care that there is gravity. That is why your weight is different on different planets and on the moon and stuff like that, is there are different gravities. Another thing is forces are vectors, and what a vector is basically it's a number with a direction. So it's like an arrow. It has magnitude and direction. So magnitude is the numerical value. That's how big it is. And the direction is which way it's pointing. So my weight is pointing down towards the center of the earth. Forces are vectors, and it's got the direction down, basically. So quick overview of forces for anyone that needs it. Free body diagrams are super important in statics. It's how you visualize what's going on. These are a couple of quick free body diagrams. The one over here is basically a box that's sitting on something and being pushed. So mg is mass times gravity. That's its weight. It's being pulled down. So this arrow here represents its weight vector. In here is the normal force, which is what we call something that is being like held up or supported by something. And it's pointing straight up because it's against the weight, and it is pointing away from the surface that it's sitting on. So it's pushing up on the thing, keeping it from falling. And then the force, the F, is for just a general force. That's something or someone pushing on this box. Over here, we have another free body diagram, which is a little bit more accurate as to what we usually actually draw. This is just a box and a ramp. It's similar. These are not labeled because it's part of a question that I pulled it from, but basically F1 is the weight. It's pulling straight down towards the earth. F2 is the normal force. It's pointing perfectly away from, so perpendicular, 90-degree angle, from the surface that it's on, which is the ramp. And then F3 is a force of somebody pushing it up the ramp. Another thing that's important in this, if you see these two arrows that are X and Y, that's the coordinate system. And you'll notice that it's tilted. The reason it's tilted is because this thing is on a ramp. It's way easier to do the equations for this if you tilt your coordinate system. And we're going to go through some of those little things in a sec, but coordinates, how you define direction when doing statics is very important and makes your life a lot easier. So typically a coordinate system would just be up and to the left. It'd be your y-axis up and down. Your x-axis is left and right. But if something's on an angle, it's nice to tilt it, and then you redefine up as away from that angle, kind of. So that's why it's tilted here. It just makes the equations easier because you have to deal with less angles. Are there any questions on that? Do not be afraid to ask questions, by the way. I really would prefer people to. Good, I guess. Cool. Moments is a moment. A torque is a kind of moment. We were talking about torques with motors. Basically, it's the twisting effort, how it's angular force. So how much something is twisting something, how strong it's twisting it. Moments are defined by, so this equation here, T equals FD. T is torque, F is force, and D is distance. And then this little symbol down here just means perpendicular, so a 90-degree angle. So what that's saying is basically your torque is equal to your times your distance. And the distance is always going to be perpendicular to the force. So here are some examples. Basically, it's down here you can see your torque is going to be maximum if you have a force applied at the furthest distance possible. So like that's why we use wrenches. If you hold the wrench at the end, you'll have more torque and be able to twist it easier. The closer you get to the thing that you're twisting, your axis of rotation, the harder it gets, the less torque you're going to be applying. And if you end up where you're in line with the axis of rotation, which is this last example over here, and your force is just going straight through the axis, you're not actually twisting anything. You're just pushing on it at that point. So you're not applying any torque because distance equals 0. So if you multiply a force times 0, 0, you know. And then this thing on the right over here is just an example that even when there's a bend, it doesn't matter. It is still just the distance out to the force itself. And then that force times that distance equals the torque that it is causing. Any questions on that? I think Jude, Maxim, and Jameson, this is all just review for you guys. Josh, I don't know if you've seen this before or not. Yes or no?
No.
Okay. Yeah, so if you have questions, just feel free to ask them. This is just general knowledge. I don't think very many people or anyone knew it going in or starting the course. So if you have any questions or something doesn't make sense, just speak up. Okay.
Okay.
Cool. All right. So that's moments on their base level. Again, any of this stuff, if you want to watch a previous lecture, they are gone into in more depth. Equations of equilibrium. This is the math part of statics. The other parts are sort of the setup, and this is the actual figuring it out. Basically, the equations of equilibrium are where you add everything together so that you can find the things that you don't have. Things to keep in mind, and this will make more sense in a sec, but split up your work. That just basically means cut things up into smaller to digest pieces, do those, and then put the answers of those together. That way you're not looking at something crazy, you're just looking at little pieces at a time. Coordinates are your friend. I mentioned that. You can change your coordinate system as long as you're consistent. Just don't keep changing it. Choose one and use that. But they are your friend. They can make your work way easier. Angles are difficult. They make your equations way longer and way more complicated. So if you can change your coordinate system to get rid of some angles, definitely do that. You want to get rid of as many angles in your equations as possible. The things that make up the equations of equilibrium, you're going to have your x, y, and z components. That just means for each of your axes, you can see your axes over here. We've got z, x, and y. And that basically means you're going to cut the vectors up into their different components so that they're straight along an axis. And then you'll have Newton's 3 laws, which for the most part is going to be F equals ma. And then you'll throw in torque as well. Those things make up the equations, and we'll see that here in a sec. So here's just some very, very easy examples, and I will draw these as well so that we can look at them just real quick. Basically, these here are equations of equilibrium, and what these would be if you looked at a free body diagram. Here's our coordinate system with our x, y, z. What this is saying, we have a tension force in the positive y. So I draw an arrow. I'm going to change to red. I'm going to change to red so that it's easier to see. There we go. We've got a tension force in the positive y direction. See, this is positive y over here. So we'll do T1. We have a tension force in the negative y direction. So we'll draw one over here. That's T2. We have a general force, so a pushing force in the positive x direction. That's this way. So we will say F. We have a friction force, which is this little f, lowercase f is friction, in the negative x direction, which is this direction. So we will label that. In the z direction, the positive to z direction, we have a normal force. So we'll put that in there. And then in the negative z direction, we have our weight. So we'll put that in there. And then what you'll notice here is there's like these weird t's. Those are taus. That tau is the symbol for torque. In the thing earlier, it showed it as a t, and sometimes they do that, but usually it's a tau because you want to differentiate tension from torque. So these ones, you can see it's the moment around the z-axis, and this one's a little hard to conceptually get sometimes, but and I'll change to a different color for it so you can see them. If it's the moment around the z-axis, that means the z-axis is your axis of rotation, so it'll be going around the z-axis. If it's positive, it's counterclockwise, so counterclockwise, and if it's negative, it's clockwise. So what we can see here, we have tau 1 is counterclockwise around the z-axis. So we'll draw an arrow going around the z-axis, counterclockwise, and we will label that tau 1. And then we also have a torque going clockwise around it. So we will draw one around the z-axis going clockwise, and we will label that tau 2. So this would be the free body diagram of these equations over here. They're not defined. These are all variables. They're just letters that represent numbers. But basically, the idea behind the equations of equilibrium is you solve each one individually to figure out certain forces. So let's just take this. Actually, let's take this z equation over here. So this symbol here just means the sum of, means you add them all together. The forces in the z direction equal, and then you add up all the forces. So we see we've got a normal force and a weight force, so that's what it is. Normal minus weight. And let's pretend that we know what the weight is. If we know that the weight is 10 pounds, we can say normal equals, or normal minus 10 pounds equals 0. And the reason I'm saying equals 0, you can see it up here as well, is because in statics, nothing is moving. Everything is perfectly balanced, as all things should be. And so everything's not moving, so you know that the overall forces are equal to 0. So what we can say is because of this, because normal force minus 10 pounds equals 0, you can say that the normal force equals 10 pounds, because if you subtract 10 from 10, it equals 0. So this is a really simple example of kind of how you use your equations of equilibrium to find the forces that you don't know yet. It's you take the things you do know, you plug them into some equations, and then you solve those equations and use those equations to find the things that you don't know yet. That is the basis of statics. It's just things that don't move. The reason it's useful for robotics is like robots falling over. If you got a big chunky arm and your robot is driving, and then you extend that arm a little bit and it gets too heavy and your robot just tips over. We've seen that in some years. We saw it at Worlds with Super 7. The first time we went to Worlds, that was a big problem for them. They would drive around and then fall over. It was really funny, but also sucked for them. So are there any questions with this? Just the general overview of it. I'm going to take silence as a no. Okay, so again, there is a lecture on statics. You can definitely go watch it if you'd like to. Let's clear. There you go. And go to the next one. This is a quick statics problem. I don't actually know if I want to do it. I'll let you guys decide. This is the last official slide, so vote yes or no as to whether or not you want to do this statics problem. Jude, yes or no?
Do we do it together?
Yes.
Then yes.
Okay, so we got one yes. Jude?
No thanks. I'm like
Okay.
falling asleep because I didn't sleep last night.
Fair enough. Maxim? Maxim, you there? Jude's falling asleep and Maxim's already asleep. Is what's going on? Jameson, what about you?
I'm fine either way.
Okay.
I understand it, but I wouldn't be opposed to doing it.
All right. So because Josh hasn't seen it before, I'll go ahead and do it. But before we do that, because Jude, I don't think you need to stick around if you already know it all and you're kind of like dipping out conscious-wise. So if we want, are there any general questions or curiosities that you guys have that I could help with or answer before we go into this problem? Because this is more of a general class. Okay. Then we're going to do this problem. Jude, if you want to stay or go, that's up to you. If you have any questions or things you're curious about, you can ask them. Feel free.
Is this the problem we did a while back?
It is. Yeah, we did do it a while back.
Okay, cool. So I'll probably leave.
Yeah, so if you want to just go watch it, if you feel like you need to, you can definitely do that. But especially for Josh, just going through a problem and asking questions for things you have can be useful. So yeah. Up to you, but we will do this problem real quick.
All right. I'm gonna go.
Adios.
Bye.
All right, so we will begin this problem. So first things with statics, what we're going to do is we're going to define where our forces are, and we're going to read the problem to do that. So we can see it weighs 15 newtons, which is assumed to be at the robot center. So we will draw a center point, and that's where the weight will be. It has an arm with a 5 Newton claw on the end. So we know that there is another weight over here. It says its wheels are 2.2 meters apart from each other. So we can say from, and I'll actually do dimensions in a different color so that we can differentiate everything. Let's say from here, the center of this wheel, that distance there is 0.2 meters. And what it's asking is how long can the arm be without the robot falling over? So basically, when you want something to not fall over, you want it all the forces to equal 0 because you want it to be in equilibrium. So that's what we're doing. So we already know that the weight of something always points straight down towards the center of the Earth. So we can draw its weight here. So it's got 15 newtons there, its weight. And we know that this weight also points straight down. It's this 5 newtons. So, all right. Josh, since you're the one who hasn't seen this before, what other forces would be on this robot? I will give the hint that there are 2 other forces that we need to put in here. Any guess is good, whether it's right or wrong. Don't worry.
Would it be gravity?
So gravity is not a force. Gravity is an acceleration. So G equals an acceleration. Force equals mass times acceleration. And the force that is because of gravity, the one caused by gravity, is weight. So it's weight equals mass times gravity. And that is this guy right here. That's our 15 newtons because we were told that it has a 15 Newton weight. So we already have weight in there. What else would there be? We have 2 downward forces, so we know that we need some upward forces. What else is acting on this robot?
The force at the ground.
Mm-hmm. Do you remember what that's called?
Newton's third law.
The normal force is what it's called. Force. So yeah, we have 2 normal forces, and it's where the wheels touch. So we're going to do normal 1 and normal 2. Okay. So those are our other forces. So what we're going to do is we're going to try to make everything equal 0. And most importantly, we need the moments to equal 0 because we're trying this thing. We want this thing to not tip over, and tipping is a rotation. So moments mean rotation. So that's what we're trying not to do. When we're doing moments, we need an axis of a rotation, something that it is rotating around. So if the robot was falling over, what would it be rotating around?
The claw.
It would be rotating around the claw. So just to show,
it
would be going around that.
No, it'd be going around its center.
Would it? It'd just be spinning in place?
No, because the claw would touch the ground eventually, and then the force.
So what's it rotating around? If the claw wants to fall down.
Oh, the wheel, the front wheel.
Yeah. So the front wheel is our axis of rotation, and we're going to say that it is the center of the front wheel. So this green dot. We can actually, for moments, basically choose any place for the axis of rotation, but you always want to choose one that helps you. And the reason this one helps us is you see how the normal force is going straight through it?
Yeah.
Well, that's great for us because if you remember, if you have an axis of rotation and a force goes through it, it gives no torque, right? Because torque equals force times distance. Distance equals 0. So torque equals 0, right? So that's great. That just eliminates part of the equation. We don't have to worry about it. And that is what we are looking for. We always want to make the least work for ourselves. So then we write our actual equations of equilibrium. And what those look like is you always have a certain set of them. You'll always have, depending on your axis, and I should actually have drawn that at the beginning. We're going to say, here is our coordinate system. So we have our x and our y axes. This is a 2-dimensional problem. We could do a 3-dimensional problem. We have done a 3-dimensional problem in the other lectures, but we're not going to do that today. We're just going to do a 2-dimensional one. And what that means is we need sum of our forces in the y direction. So that's one of our axes equals 0. And we need the sum of the forces in the x direction, which is our other axes, to equal 0. And then we need our moment, because we know that this thing could tip. So moments, and I said this is 2 dimensions. Technically, it's 3 dimensions because there's a z-axis pointing in and out of the page, but you don't really worry about it. We just say it's rotating around this point. But we will say moments on the z-axis through this equals 0. So now we just need to write these equations out. So for the F equation, we need to write all the forces in the y direction. Sorry, no, for the y equation. Somebody want to throw out one of those forces? So these are forces that are pointing either up or down.
The 15 newtons down from the center of the.
So would it be positive or negative? The 15.
Negative.
Yep, because it's down. It's going against positive y, so we'll do minus 15. What's another one?
The 15 newtons going down again, so it'd be a negative.
You mean the 5 over here?
Yeah.
Minus 5. What else?
The 15 newtons coming up from the wheels of the opposite force.
Well, these ones aren't defined as 15 newtons.
Okay.
They are just in. We don't know what they are. And what we're actually trying to figure out is we're trying to figure out the ins as well as this distance here, because that's what it's asking, how long can the arm be. So this is what we're actually looking for. But for being thorough, I'd like you to also find the normal forces. And I will draw actually this as distance d is what we're looking for. All right, so what else? These normal forces you said, so normal 1 plus normal 2 because they're both going up. Okay. What about the x direction? Do we have any forces going in the x direction?
No.
Exactly, so it's just 0. We're good. Moments. This is a little more complicated. We got to write all the moments that act on this axis that we chose. So what we do for that is we look at all the forces and we multiply them by their distances away from the axis of rotation, which is for us this green dot. We say normal 1 is going through the dot, so we don't need to worry about that one, but all of the other forces we need to worry about. So let's start off with our 5 Newton weight force over here. What is that going to look like in this equation?
5x or 5nx, because we don't know the distance.
So we're calling our distance here d, so we'll do 5d, so 5 times d, and is it positive or negative?
Positive.
Yep, because it is going counterclockwise. What about our normal force over here? What are we going to write for that one?
N1 or N2, or wait, no, multiplied by how far away it is. So N2 or 0.2 N2.
Yeah, so we can write it whatever order we want, but yeah. And is it positive or negative?
Negative.
It is not. It's positive. It is rotating this way, which is counterclockwise. So it's positive. And then what about our weight force here?
That would be 15. Are we assuming that it's 0.1 meters away?
The reason we are is we're assuming the wheels are, so the wheels are equidistant, and it did say center of the robot, so we are putting it right down the middle.
Okay.
Yes, so 0.1, so times 0.1.
Yes.
And is it positive or negative?
It'd be, since it's right on the axis of rotation, it's neither. Or
It
no.
is not on the axis of rotation.
No.
It's here.
It would be counterclockwise, or no, it'd be negative.
Negative because it is clockwise, correct. Okay. So there's an interesting thing about this problem in particular that makes it much more easy. What we just did is set up our equations of equilibrium. And if you look, this equation has two variables and this equation has two variables, right? So
Yes.
we can't actually solve the equations right now because we don't have more equations than we have variables of the same in number. So right now we couldn't really solve it. But because this problem, and I'm going to scribble out x because we don't need to worry about it, because this problem is the kind that it is, we can do a certain thing, which is this is at the moment that the robot is about to tip over. We're looking for the very edge case, right? So what we can say is when the robot is just about to tip over, N2 is a lifting off of the ground. That wheel is about to come off the ground, right?
Yes.
So we can say that N2 actually equals 0 because it is so small that it is not actually contributing anything. Right now, that means the whole robot is balancing on N1, okay?
Yeah.
So it is just about to tip over, but it's not yet. So N2 equals 0. So what we can do is we can actually just cross out all the N2 terms because they're all going to equal 0. You know, multiply something by N2, it doesn't matter, 0.
Yeah.
We just cross them out, which means we can now easily find our new equations. So we'll say Fy equals 0 equals N1 minus 15 minus 5, and Mz equals 0 equals 5b minus 15 times 0.1. So from these, what is N1? We solve this equation.
It would be 20. So Fy would all equal 0 because
Yeah, so Fy equals 0. This is sum of Fy. So this thing here doesn't actually matter. This means the same thing as this. So
yeah, so that equals 0.
Yep, so this all equals 0.
And then 5d would have to equal.
Well, so what first off, what is N1? What is the value of N1? If N1 minus 15 minus 5 equals 0, what is N1?
It would have to be 20.
Yep, so N1 equals 20 newtons, so we got that one. And then, yeah, let's find D. So we know that 5D minus 15 times 0.1 equals 0. So if we do 15 times 0.1, you just need to move the decimal over 1. So it's 5D minus 1.5 equals 0. So then you can add 1.5 to both sides. So you get 5D equals 1.5. So then you divide both sides by 5, and what do you get? What is D?
Divide both sides by 5, it would be 3.
1.5 divided by 5.
0.3.
Yep. So 0.3 meters. That is how long this arm can be before the robot tips over.
So about a foot.
But that would be like, well, if you moved and you had an arm that long, it would tip.
Yeah. So that is an important thing to note. And so what you found here is this is the very maximum length the arm can be before the robot tips over, right? Say you want your arm to be longer than that, or you want to be able to drive, because if you drive with your arm this length, as soon as you drive forward and stop, your robot's going to tip because it's going to have momentum and push itself over, right? So what we usually do is we usually do something called a safety factor, which is a number that is, there is a way to calculate it for certain things, but usually we just choose one. It's easy to choose a safety factor of 2. And basically what you do is you take your maximum value, which is this case 0.3, and you divide it by your safety factor. So max divided by a safety factor equals new max. And so what that would be here is 0.3 divided by 2 equals 0.15. And this would be your new maximum, a maximum that you feel safe with, right? So if you drive with this maximum, you're not going to fall over. If you want your arm to be longer, though, there are ways to fix that. So like, let's say we calculate this and we see that 0.3 meters is our longest arm, which is like a foot. It's not very big. You know, maybe you need to, like a relic recovery year when we needed to put that guy all the way out the end of the thing. Maybe you need a 3-foot long arm. A way to fix that is if you just put a bunch of weight in the back, you'll offset it. But the good thing is that if you want, you could basically do the same equations but backwards, where you say, here's the length I need my arm to be. I need my arm to be 3 feet, right? And work backwards to find how much weight you need to put in the back. Okay? So maybe it's a year where you need a really long arm that has to hold something heavy, but you also have to climb. And your motor can't, your robot's already on the edge of what your motor can handle lifting wise. So what you do is you do equations to find the exact amount of weight you need to put in the back of your robot to keep it from tipping over, but that way you keep it at the lowest amount that it can be for climbing. Does that make sense? So those are some applications for these sorts of equations. This was a general easy problem for them. If you want to know how to do it like better, or you want to learn more about it, then there is a lecture on statics, there is a lecture on equations of equilibrium, and there is a lecture on moments and torque. So if you want to watch those are great. There are problems that if you want, you can like pause through them and follow along and work them out yourself. And I explain them and work through them as well. So that is a good resource to just go check out.
Okay.
So that is kind of the end of just the general overview-y stuff. I will go ahead and clear. Get out of that. And we will stop that boy. So does anyone have any general questions?
None here.
Anything that you just want to know about?
Not necessarily.
Okay. I'm not sure what we're going to do in terms of this class or classes in general with this. I'm going to talk to Kyler and Mr. Smith about what the plan going forward is after this class. But if you guys have anything, and you should ask other people in the post as well, if you have anything that you specifically want to learn about or want taught, then you should let one of the 3 of us know. And we'll try to work that in some way. But I think us 3 and others are willing to teach things depending on our skill sets and stuff. So if you have stuff that you want, well, let us know and we'll try to put it in there. Yeah, I think that's all that. I am going to do another class next week. It's going to be more of the motor stuff, and we're going to be doing motor performance mapping. So that one's going to be kind of math heavy. It's all easy math, but it is a little, like there's more math and tables and stuff. So if you want to know more about motors and how they work, that's kind of what that's going to be over. And also how to run them at their peak efficiency, which means they're going to last the longest amount of time and give you the best output for what you're putting in. It's really useful for a lot of things. The main use for it in FTC is that you don't kill your motors so fast, which I know the committee and adults will like because that means they don't need to buy any new motors. So it also looks really good in a notebook if you do that kind of stuff.
Did you hear about the new notebook, David?
I did. I don't know if they're going to keep that past COVID stuff. I know they're doing it for the quarantine year, but I assume the notebook's going to go back to being normal once that all ends. So, a good thing I think in these new notebooks though, because I did engineering notebooks for engineering class in high school, and they were an actual what you guys do notebook wise is not an actual engineering notebook. It's more of like a journal about like what the team does, which is really good, but it's not an engineering notebook. An engineering notebook is basically just calculations and drawing designs and stuff like that. I think a really good thing to have in this notebook this year, because it's smaller, is gonna be just a page of like all sorts of like calculations, like mathematical stuff that you've done, and the actual work that you put into engineering the robot. So if you just do these sorts of calculations for whatever robot you have, you don't even have to necessarily do them to build the robot, but if you do them at some point and you show that you have them, I know there's an award, I think it's the design award for the calculation section of your notebook, that in the design section. I'm pretty sure judges will eat that up. So recommendation. It's maybe an hour's worth of work to do all of the calculations that you would ever need for an FTC robot. So yeah, so if anyone has questions, I'll stay on for a sec, but if not, I think we're good to go for today's class.
Well, bye.